You're good to go.
All right, welcome everyone. This is Unit 4, Sprint 1, Module 2. Today we're going to be talking about vector representations of text. So today's a little interesting because we're going to move away from looking at words and looking at a whole collection of words across a whole collection of documents to shifting to begin to look at individual documents and representations of individual documents. So if you think about how to understand what's in an individual document, whether you're using that for a classification task or a unsupervised learning task or something even more advanced, you need some way to represent a document numerically. Why? Because machine learning algorithms can't interpret raw text, right? We can't do dot products and linear algebra and fit decision trees on strings. We need some kind of way to represent text as a number. That's what today's lecture is all about. What are a couple of the big ways to represent text as a vector or as some kind of numeric representation of raw string? So let's go ahead and hop into the notebook. So our learning objectives today are going to be three-part. We're going to represent a document as a vector. We're going to represent a document as a number or as a series of numbers. In part two, we're going to learn how to query a collection of those vectors for similarity. We want to find things that are similar. We're going to build a very basic content-based recommendation system. Then in part three, we're going to talk about how to apply word embeddings to create document vectors. So I'm going to show you three different types of document vector representations today. The first two are in the first learning objective. The last one is in the third learning objective. And I'll talk about the difference in just a second. Now, today, I also want to show you a little bit of a case study. So let's start to think about this in more of a real world context. Let's say that I'm on the data science team for the BBC. And on the BBC's website, there's a lot of information, but we're mostly concerned with the news. And in particular, we're concerned with technology. Now, the editor of the technology section of the BBC News site is really interested in engineering a new feature on different articles. They really want to, here's a nice article about Zoom bugging. They want to engineer a feature where it says related topics to provide recommended articles. Similar to More on This Story, they want to be able to add kind of suggested articles here instead of related topics. So what we're going to do is we're going to read the whole text of this article. We're going to process it into a vector, and then we're going to look for other vectors that are similar to this one. And that's how we're going to operationalize providing those recommendations. Now, we're not going to go quite so far as coding that in HTML or Flask or anything like that. We're just going to get to the model portion of it today. You hopefully have a good grasp on how to do this in Flask as well now. All right, so let's talk about how to represent a document as a vector first. So what we're going to do is we're going to create a thing called a document term matrix, a DTM. Each column is going to represent a word or a term, really, and then each row is going to represent a document. Now, the value in each of the cells, right, in that matrix could be a range of different things. The most traditional is the count of appearance of words. How often does that term appear in that document? Does the term appear at all? Binary, true, false. And term frequency, inverse document frequency, what's called a TF-IDF score. Those are the three traditional ways of counting the words inside of a document term matrix. So let's say that I was just doing a classification task, and I was going to use this document term matrix, and I was going to classify the documents as about Zoom or not about Zoom, similar to the article we saw. That approach would work, right, if I had a couple, maybe 2,000 or 3,000 articles, maybe 50% of them were about Zoom, 50% of them weren't about Zoom in the training data set. That classification would work. but we lose context and grammar. Why would it work? If you had to pause and think about that for a second, why would this approach of counting the occurrences of words work in something like a classification task?
By getting a count of the words, are we able to give the algorithm a choice to determine when it's hit the threshold between where 0 and 1 would be? So it only has to, pick one side of the coin or the other.
Yeah, but the algorithm would do that naturally anyway. I guess what I'm saying is from the perspective of features where we don't have any information about the context of the article or the grammar of the article, how are we able to distinguish the articles between one category and another category? What is it about the features?
You're not saying total word count. You're saying like what we did yesterday, right?
Mm-hmm. What we did yesterday, but for each document.
Okay. Is this like I feel like it's really simple. It's just like the ones that talk about video and the ones that don't? Or is it?
Yeah, exactly. So let me give it to you like this. If you think about, if we're trying for the two classification problem, and we've got a couple thousand articles that are about Zoom and not about Zoom, the reason that this classification model would potentially work is because we use different terms to talk about different things. So the terms Zoom bugging, all these additional terms are going to appear more often in those articles than they are articles that are not about Zoom. So really just the count of word is kind of that intuition behind why we can ignore grammar and context. And why do we do that? Because it's more complicated to include it. It's more complicated to start to process the context and the grammar. It's not impossible with modern deep learning approaches, but the count of words is a really solid approach. Let me show you with a little bit more real world example in the code, which I think will help tie things together. We're gonna import pandas seaborn. We're going back to scikit-learn today. So each day we're almost introducing a new library a little bit. Yesterday we talked about Spacey. Today we're gonna talk about scikit-learn. Tomorrow we're gonna focus on scikit-learn again. And Thursday we'll talk about Jensen. Hang on just a second. I forgot to change my kernel just to make sure that mine's identical to yours. All right, so I've got this sample text. We're going to skip over this warm-up exercise for the moment just to extract tokens. So one of the things that happens, if we're going back to our BBC example, and we're trying to engineer that feature on the BBC website, a common way to ship text data is that you'll see text data sent not in one CSV file, but in a directory. So you'll get a whole bunch of individual files that'll be a document. So you can see this, we'll scroll like this. So like this is one observation, this is another observation, this is another observation. Okay. It doesn't mean that you can't ship text data in a CSV or any other file format. This is just a common way that it comes. So we need some kind of function to help us process the data. So I've written this nice function, gather data, that's gonna list the files in the directory, loop over the files, make sure it's a text file, and append the data to one list. There's also another function called glob, which could help us do something similar. But we won't go into that right now. So we'll gather up the data, and then now our data is in a nice list object. So in order for us to turn this data into a document term matrix, what we're going to do is import something from scikit-learn.featureextraction.text called count vectorizer. So pretty much all the stuff that you're going to care about under .featureextraction.text, there's count vectorizer, tf-idf vectorizer, and there's a third thing called hash vectorizer, but don't worry about it right now. Its use cases are pretty specialized. So we're going to take this list of text documents. We're going to instantiate our text count vectorizer. We're going to fit that vectorizer on our text and then transform it into our document term matrix. I'm going to go over each of these steps in a little bit more detail. So the code's written out here, but we'll talk about it. So our vectorizer in the .fit statement, so after we instantiate it, what this does is it learns a vocabulary. See all these fun stuff down here. There's a parameter called get feature names. And these are the features that learn from our sample sentence in this list text. We'll come back and do data. Okay. So when we call on the fit statement, we just learn this vocabulary. We don't do anything else. Then when we call the transform statement, what happens is our data is actually now transformed into a matrix. But it's not a matrix that you have seen before. It's what we call a sparse matrix. And this sparse matrix is, it's not sparse in the sense that it's full of zeros, but actually the way the data is stored is a little bit different. So here what we're looking at are the index locations of a word in a document. So this, on the far right, we're going to go right to left. Right is the count of a word over here. This is the term, so word 4 has a count of 1 in document 0. Now the reason that we store information in this kind of column-based sparse matrix is so that we're not storing a bunch of 0 values. And Jonathan's spot on, right? So we're saving it like this so we don't store a lot of 0 values, just storing the non-zero values. But the only downside to this storage format is that it doesn't play nicely with a lot of machine learning algorithms. You need that dense matrix for a lot of machine learning algorithms. There are some that'll play nicely with a sparse matrix. I think naive Bayes actually plays pretty nicely with that in scikit-learn's API. Right. And so if we trace back, okay, so our vector feature names and our text, we can go and look up an individual word. Documents 0, word 4, count of 1. All right, so documents 0, this is this one. Word 4, 0, 1, 2, 3, 4. Word right? Okay. Well, this is kind of a tough way to visualize information. So I like to transform this back into a dense matrix, and then we can turn it into a data frame. So we can get the word counts for each document, turn the document term matrix to dense, And then to get the column names, we do vectorizer or vect.get feature names. And so now we can see document 0, the word by appears once, the word content appears twice, so on and so forth. Christopher was asking about the type. Christopher, I've already written that over. So let me see if I can rewrite it. Yeah, the two dense, you get matrix because it's transforming that to a dense matrix. But if I eliminate the two dense, I'll get a SciPy sparse matrix. All right. Let me pause here. Are there any questions so far?
I actually don't understand the cell 11. Elaborate on that again, please.
Mm-hmm. Yeah, so what you're looking at is each row represents a document, each term represents a column, and each cell represents a count of this term and this document. So the word as does not appear in document 0 at all. The word by appears once in document 0, the word content appears twice in document 0. So our data from the BBC is about 400 characters long, or excuse me, 400 observations long. So we just transformed a tiny sample text. We're going to run the count vectorizer over that entire data set now. From scikit-learn.featureextraction.txt, import count vectorizer. Now count vectorizer takes a number of parameters. So we can pass some fun stuff to it. It has its own list of default stop words. It has max features, which are the 1,000 most or n most common features. There are also some other fun parameters that we'll start talking about. Let's take a look at some of those parameters. So some of the big ones, most Python, by the way, and text data, I would be remiss if I didn't mention encoding in a week about NLP. Most text data out there is encoded as UTF-8 nowadays. Python 8 is by default in UTF-8. If you're dealing with files that come from like Microsoft Word, stuff like that, sometimes they're encoded as Latin 1 or ANSI, which is a text encoding where the set of possible characters is limited to basically just American English. UTF-8 includes things like special characters that you might encounter in other languages like French or German, etc., as well as things like emojis, right? UTF-8 is a standard for how to encode text.
Does it include like Mandarin characters or Arabic?
I'm not really sure, Taylor. I'd have to look that up. My guess, if it does include Mandarin characters, it would include simplified Mandarin. I'm not sure about Arabic though. Okay. So some of the stuff that we can add to the count vectorizer, we can convert everything to lowercase. It's but true by default, right? Principles of good tokens. We can also customize the tokenizer, right? When we saw that document term matrix that was magically created, we saw that scikit-learn has its own vectorizer and tokenizer that are being used under the hood to create those columns. So if you wanted to, we could customize the tokenizer that we use. Some of the other parameters that we can specify, max and min df, which exclude words that are at the top of the frequency and at the bottom of the frequency. So if I have a word that appears in 99% of documents, I'm going to exclude any words that occur beyond that. If I have words that appear in less than 5% of documents, exclude those from our vocabulary. Right. So 2 questions I'll answer real quick. Jesus asks, curious why we're getting these outputs with bytes formats when running data 0, 25. Not sure, actually. Yeah, but the B definitely does mean bytes. It's probably with how we read in the data in our gather data function, Jesus. Second question, Christopher asked, can you give some use cases for customizing your tokenizer? Absolutely, yeah. So if you wanted to use more sophisticated tokenization for, like, let's say you wanted to do limitization, Spacey is not doing, scikit-learn is not doing limitization by default. So if you wanted to do limitization, you might customize your tokenizer to use Spacey instead of using scikit-learn's default. That would be one use case. Another use case might be, let's say that you had some kind of special pattern you were looking for in the text that you wanted to extract, stuff like that. Actually, I'll give you guys a hint for tomorrow on customizing your tokenizer. So tomorrow's class, we're doing a document classification problem. If you wanted to customize your tokenizer to extract only a limited vocabulary, you could add another parameter to your count vectorizer called vocabulary, pass it a list, and it would only extract those things. Could be helpful. All right, so let's go ahead and fit a new count vectorizer on our BBC data. So instantiate with some parameters, stop words equal English, max features equal 1,000. So we're going to learn a vocabulary. Then we'll fit that, fit and learn the vocabulary, transform the data into a document term matrix, and we'll plop it in a data frame just to visualize it. So just for clarity here, the reason I'm putting it in a data frame is so we can inspect the results. We don't necessarily have to have it in a data frame to do modeling on it or anything like that. The data frame is just to help us see what's happening. All right. So here's our document term matrix. Oh, getting some messy features in here. Whole bunch of numbers. Right. Worldwide, worm, worth, writing, Xbox, XP. Lots of features happening. Well, you'll notice that most of these features, let me do a little bit bigger here, that most of these values are 0. But then all of a sudden you'll see the occasional term that'll pop up and it'll be like, oh, there are 5 instances of this term in this particular document. Okay. Or you might find one with 20 instances of the same word. What happens is all of these documents are different lengths. So if we were to visualize the length, there's a type mean somewhere around 2,500 characters. But there are a few documents way out here to the right that are a little bit longer. So if these counts pop up, if I've got counts of say 5, 10, 15, 7, 20, then if I have one document that's, let's say it's about the Xbox, and I have, and maybe a couple game names and a couple other gaming terms that have counts. But let's say one article is maybe 2,000 characters longer than another one. In most machine learning models, you're going to have a hard time distinguishing between those two observations because they're further apart in space. So a good way to think about this is if you isolated it to maybe just 2 terms, and you said, what's the count of Xbox and what's the count of PlayStation? And you're going to end up with one observation where the counts are like 10 and 10, that's really far out, and another observation where the counts are 2 and 2. And if you're trying to learn how to distinguish between, say, a third observation, your model is going to have a hard time learning the decision boundary because the observations are far apart in space. So you need some way to control for the relative frequency of terms in a document. Enter term frequency, inverse document frequency. So count vectorizer works really well. It's like one of the classic methods for text feature extraction, but TF-IDF is much more common in practice. And the reason is because TF-IDF controls for what's unique to each document relative to that term's uniqueness across the corpus. And the scores are normalized between 0 and 1. So for any given term, you're going to extract a score that's going to be between 0 and 1. So there are 2 components, term frequency. What is the frequency of this term in this document divided by the total number of words in the document, times the inverse document frequency, which is the log base 2 of the total number of documents with that term. So if a term appears pretty much only in that document and it appears pretty frequently, the score is going to be close to 1. If the term appears pretty much in all the documents, the score is going to be closer to 0. And that's how you kind of begin to distinguish what documents are about. So how do we do TF-IDF? We actually don't need to do anything too special other than just import something else from scikit-learn. From scikit-learn.featureextraction.txt, import TF-IDF vectorizer. The protocol works the same way as it did for the count vectorizer. Import, instantiate, fit, transform. Right? It's the same for any feature extraction method in scikit-learn. Instantiate, import, instantiate, fit, transform instead of fit, predict, like you're used to seeing in most machine learning models. They share a lot of the same parameters. TF-IDF has a couple more parameters for tuning some of the TF-IDF stuff, but things like stop words, max features, min df, max df, all exist within TF-IDF. The other thing that you can do, which you guys have seen before with fit predict, is that you can fit and transform the same step. So this is useful when you're dealing with training data, right? So you're going to train your TF-IDF vectorizer on your training data and then use the TF-IDF vectorizer on your test data, right? So you're going to learn the vocabulary from your training data. You're going to apply it to your test data. Okay. So I applied the TF-IDF to our BBC data. Now the scores are looking a little bit cleaner. I increased the max number of features, by the way, so that's why some of the words at the end are a little bit different. But now the scores are much tidier. Well, what if we wanted to customize this? What if I wanted some limmatization? I'm getting younger, youngsters, young. Let's clean it up with some tokenization with Spacey. So I'm going to take the lemmas from the token in doc if the token is not a stop word and the token is not punctuation. We then also want to exclude pronouns, but that's okay for now. One of the other parameters that we want to pass, in-gram range. This is a new fun thing. So instead of looking at single terms, what in-gram range is going to do is extract multi-word phrases. So let's say that text data machines was a series of tokens that our Spacey tokenizer extracted. What the in-gram range will do is extract the combinations text data, data machines, text machines. So it's going to extract these multi-word phrases. Now it's going to scan each document, extract the multi-word phrases, and then count the number of occurrences of those phrases against the total like max features. Okay. The other things that we're going to actually set values for this time are max DF. So anything that we see that occurs in more than 97% of documents exclude. Anything that occurs in less than 3 documents also exclude. So both min-df, I think, makes a little bit more sense to use an integer value, which is the number of documents, but this also accepts a float value, which would be a percent, let's say less than 5% of documents. All right. Let's go ahead and fit predict and see what happens. Fit transform, excuse me. Now you'll notice this is considerably slower, and that's because our tokenization function is now using Spacey limmatization, which is by nature more computationally intensive. Okay. So we extracted 8,218 features. And it looks pretty interesting. We got some price information in here. Airline, announce. $2004. So our features, there are a lot of them, way more than our input documents. It's a common problem in text and in natural language processing, where you're going to end up with way more features than observations, or just a lot of features. And so you need some kind of dimensionality reduction technique to help you process the data. That's something we'll talk about a little bit tomorrow, but I just want to point out, right, the difference, the ratio between features and observations. Okay. So what we've seen in this learning objective two ways to extract vectors from raw documents, one count vectorizer and then two TF-IDF vectorizer. The count vectorizer counts the occurrences of terms in a document. TF-IDF scores a term's frequency and controls it by the inverse document frequency. Right? Two ways to represent a document as a vector. Any questions on TF-IDF or count vectorizer?
Could you say what you just said one more time?
Totally. So we learned two vector representation techniques in this learning objective. One is count vectorizer, which counts the occurrences of terms in a document. Then we learned about TF-IDF vectorizer, which scores a term's frequency in a document by that term's frequency multiplied by the inverse document frequency.
So those zeros on that TF-IDF, they could either mean that that word is everywhere and therefore it's noise, or it could either mean that it's just not in that particular document at all, like where ability in document 0 says 0.0. Could that mean that just ability is not in there at all?
Right, exactly. Yeah, if it's 0, it's probably not in the document at all.
But it could also be close to 0 if it's like in every document.
Exactly, yep.
Okay, thank you.
And Cooper, I think that answered your question as well. I will say most of the time you're not actually going to be interpreting the score of any individual term because it's a feature extraction technique. So most of the time you're going to extract this and then use it in a downstream machine learning algorithm. So whether that's nearest neighbors like we're about to do, or whether that's document classification like we'll do tomorrow. All right, so we're at a really good place to take a break. So we'll take a 7-minute break. When we come back from the break, we'll talk about how to start querying these vectors by similarity and really get at that BBC use case we were talking about earlier. All right, let me go ahead and start the timer. All right, see you guys in a few minutes. All right, everybody. All right, so before we continue on to the next learning objective, any questions from the previous section that you guys have arrived at over the break?
The n-gram parameter that looked for word phrases that were one word or two words. That's what we said. And we call those terms, right? Or phrases.
They're actually called just a one-word phrase would be a unigram. A two-word phrase is called a bigram. A three-word phrase is called a trigram, so on and so forth. So typically people just call like the process of extracting n-grams just n-grams. I would never, by the way, go beyond a range of 1 through 3. Like 3 is definitely pretty much a maximum. You could add this to whatever you wanted, but at that point you'd be extracting like whole chunks of sentences.
Could you really quick too just briefly go over the interpretation of the sparse matrix?
Mm-hmm. So the sparse, let's go back. So just for awareness too, there are several different types of sparse matrix. So when people say sparse matrix, typically this is what they mean, where your matrix is literally full of zeros. This is a special case of a sparse matrix that's designed for data storage. So basically what it does is it only stores information that's non-zero. So in document 0, term 4 within the vocabulary has a count of 1. In document 1, term 14 within the vocabulary has a count of 1, so on and so forth. Then if you wanted to, for most machine learning models, you'll want it in a more traditional dense format where all the zero values are explicit. And then you can just call in the toDense command to transform it into that format.
Sweet, makes sense. Thank you.
No problem. Let's move on into our second learning objective. So we're going to query documents by similarity. So we're going to talk about content-based recommendation systems. So if you've ever thought about how a search bar works, like how Google works, how a search bar and your email works, right? You know, it's an information retrieval problem. You have a search parameter, you're trying to retrieve information. Now, it's not simply matching your text against the input documents in things like Google, stuff like that. And there are numerous, and I mean numerous, ways and schools of thoughts of how to do information retrieval. Like the way Google is entirely different than what we're talking about today. But one of the very classic, easiest conceptually, is to take the input document and treat that as our search. So we're not really using a search bar. Instead, what we're doing is we're just querying by the whole document. You could think about it like you would in a library. It's like if I wanted to know which book was the most similar in a library, I might read the book and then I might go look in that section for other things that are similar. It's content-based recommendation. Right. Well, how do we do this? How do we operationalize that? Well, number one, we need some way of turning the document to a vector. Okay, check, we've got that. We're going to use TF-IDF. Then number 2, we need some way to measure similarity. We're going to use cosine similarity. Why? Because that's absolute distance between two things, or essentially some slight difference in interpretation of absolute distance. Now, similarity, we're going to measure with cosine similarity. You could also just use raw distance instead of similarity. How far apart are the observations? And then when we get to the modeling-based approaches, we're going to start to create probabilistic understandings of what the similarity could be. So the first approach, we only have 401 documents in our BBC example. We're just going to calculate the brute force similarity between one document and all other observations. So from scikit-learn.metrics.pairwise, you can pass this matrix, an input matrix, and it'll do all observations against all other observations. Pretty nifty without you having to write any kind of crazy for loops. We're going to turn those results into a data frame. Our matrix is 401 by 401. No surprise there, right? One document against all other documents. All right. So let's take a look at the first article. By the way, I think I mentioned this, but the articles in the BBC News dataset are about 10 years old. So I think some of them are like 12 to 15 years old. So this stuff is a little dated. And so our first article, mobile phones rack up 20 years of use in the UK. This is the first article. If I wanted to retrieve the similarity of one document to all other documents, I just grab a particular column or row. And so of course, the similarity of the first document to itself is 1. And then I get some other similarity information. If I wanted to know what the most similar document was, I'm going to grab everything excluding the first observation, right? And I'm going to sort the values by their similarity. So it looks like document 92 is the most similar, followed closely by document 297, document 300, document 187, so on and so forth. All right, so remember our first document is about mobile phone usage. And our next documents, I don't know what it's about. Let's find out. 92. Finding new homes for mobile phones. Okay, I see you being about mobile phones. Pretty cool, right? You just created a content-based recommendation system. It's very simple, but it works within our training data. That's pretty impressive. There might be a couple problems with this approach. Can anyone think of any problems to this approach? Okay, yeah. Two documents could have the same context but different opinions, but maybe that's not a problem on if we're trying to recommend articles. Yep, Jonathan says any new articles would have to be added to the entire similarity matrix, which means that we'd have to recompute the similarity matrix every single time a new article is written. Yes, big data frames require a lot of RAM. Let's say that I'm the BBC. I probably have hundreds of thousands of articles that have been written over the history of the BBC. If I'm trying to calculate the similarity of all those articles, that's going to eat up a lot of memory, more than would fit on any single machine or any single server. And let me tell you what, I've run into this problem myself. I was doing some analysis one time comparing the similarity of sentences in about 40,000 documents and eating up about 64 gigs of RAM on a server, trying to crunch one of these similarity matrices for an analysis. It's easy to do. This approach works, but it's computationally inefficient. Why? Because it takes up a lot of memory. You have to hold the similarity matrix in memory. And two, you have to recompute the similarity matrix every single time you add a new document. So the more and more documents, the harder and harder it is to compute, the more and bigger the RAM requirements. So with 400 documents, it's pretty easy. But beyond that, you're going to need something a little bit more robust. Inter-model-based approaches to storing similarity information. So there's one that you've already seen. You saw this as KNN. You probably saw this as KNN classifier, although it could also be used for regression. But if you just chop off the K and we just said nearest neighbor, basically nearest neighbor models are going to address the computational inefficiencies of brute force. They're going to use a couple combinations of things to help us store some information about the similarity. They're going to estimate some kind of tree-based algorithm to help traverse the space. Basically, if you think about all of these terms as points in space, what these algorithms are going to do is map and draw roads and forks in the roads within the space to help pick which points are the most similar. You don't really have to know so much about how these algorithms work underneath the hood. I think that's relatively unimportant unless you're working on one of these applications at work, and then you might want to read up on it. But just know that you're going to want to use a model-based approach to return most similarity and recommendations. Okay. Now, the two most common ones that you're going to see are parameters within the nearest neighbors model. One of them is called ball tree. The other one is called KD tree. They both work pretty well. All right. So just a reminder, this is our current document term matrix. So in order for us to fit the model from scikit-learn.neighbors, import nearest neighbors. There's really no hyperparameter tuning for us to do here. What we're going to do is we're going to fit nearest neighbors where n neighbors equals 5. This will essentially be the default return search value. We're going to use KD tree, but you could also switch this out for ball tree. Actually, we'll go ahead and do that just for shiggles. Right. Now, I printed out the model so we can see some of the stuff that's happening underneath the hood. The metric here, Minkowski, that's going to be our similarity metric. Although technically it's not similarity, it's distance. Minkowski is a type of distance. But they get at the same idea, similarity and distance. You might be familiar with some of the other distance metrics, like Manhattan distance, Euclidean distance, cosine similarity, Euclidean distance are related to one another. Sometimes you'll hear taxi cab distance, which refers to Manhattan distance. It's a couple of options that you can play with. For our use case, this is not a parameter that will really change much in terms of the search results. You might get some differences in articles in some of your searches, but for us, most of the time, this won't really change much. All right, so our nearest neighbors model is fit. So now, if I want to pass a search, all I have to do is do nn.kneighbors and pass it a search parameter. We're going to pick from our document term matrix the first row, and we're going to get the values out of that row for our search. Remember, this is a data frame. Data frame.index location 0, the values of that row. What the kneighbors returns is a list of the similarity or distance between the search and the articles that it's matched with. And we find out for the first time that article 0 has a copy. Article 62 and article 0 are the same. They have a distance of 0. But then our results from before are validated again. Article 92, also about mobile phones. Article 297 and 300, also about mobile phones. All right. Let's try another article. Someone want to pick any number between 0 and 400. First person in Slack to drop a number between 0 and 400, we'll do another query. All right, 7. Okay, we'll try 7 and 200. So Article 7. Article 7 appeared in our search results as being similar. Article 79 seems to be the first closest. So what is Article 7 about? UK games. Something about a game studio. What is Article 79 about? Oh, also about computer games. Pretty nice, right? Okay. Our model's working. Our model's working. Let's try 200 now. All right. So all right, so 200. Oh, it looks like this is pretty close distance. So what is Article 200 about? Printer ink cartridges. Okay. And what is Article 388 about? Let's find out. Looks like a reprint of the Article 200, but because the distance metric is pretty low, there must be some kind of change in that article. Probably pretty minor, maybe like a couple sentences were changed or something like that. Yeah, your articles can be different if it's read in your directory a little bit differently. So the gathered data, because we're using the index location in the list to navigate between all this stuff. So if you're getting different results, it's just because the documents are indexed differently, which is okay. Your model should still work. Okay. Well, let's just try a completely random article. Let's go, I like the Washington Post. go to the Washington Post. Let's go to tech. We'll go to video gaming. I feel like that's maybe interesting. We're going to grab the text of this article. I'm just going to grab the first 3 paragraphs. Excuse me.
Bless you.
Thank you. And we're going to take this article that I just copied and pasted and put it in this list object. Okay. Random article that we grab from the internet, not in the training data. So the first thing we need to do to query and see what's similar to this article, we need to transform the article. Okay, so it's a sparse matrix. So we're going to query nearest neighbors.kneighbors to new to dense. All right. And we see document 140, document 79, document 86, 71, so on and so forth. They're all similar. All right. And it looks like we already know document 79 is about video games as well. Document 140 also appears to be about video games. And in particular, role-playing games, which you guys may or may not be familiar with the article that we copied and pasted, but it's about Final Fantasy, which is a role-playing game. So that's good, right? We just build a recommendation model that can return articles from data that's unseen. It doesn't have to be in our similarity matrix in order for us to recall other articles that might be similar. Okay. Let me pause here and ask for questions. Do you guys have any questions so far?
The first array that you get when you're looking at the values of the nearest neighbors, that's how close it is?
Here?
Yes.
Mm-hmm. Yeah, so the first array is how close it is. The second array is the index location of the article. So distance, and then the article that's most close. So they match up here, 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 here. So Wesley asked, when we pass out a new article, it's not actually included in the model from that point forward, is it? So if we were to try a very similar article to that one, it wouldn't recommend it.
And right. I tried to ask almost the same thing.
Yes. So how do you guys think? I'm going to flip the question back on you. How would we address that problem? So if the new article isn't included in the original model, what would I have to do to include the new article? Yeah, I'd have to retrain. Exactly. And that's okay. Recommendation systems are constantly being retrained. That's part of how they work mechanically. So the thing is, the retraining process is more efficient though, because you're not fitting the whole similarity matrix. You might update the recommendation system on a nightly basis, right? When people aren't on your application, when there's like low stress, or it could be automatic. Anytime a new article triggers a job, there's a bunch of different ways to do that. But that relies heavily on some data engineering aspects. But you would have to retrain to include a new article. Now, what would happen if I tried to search for an article that was entirely unrelated to my training data? Entirely unrelated.
It might just latch onto similar words that happen to be in other articles.
Okay. Yep, that's a possibility. Let's go find out. We'll go back to the Washington Post. Let's do something that's not COVID related, because that's maybe kind of depressing. We'll do food. And we'll just pick this article. Right. So there's our article. Transform it again. Right. So we got some similar results, actually. Got a couple articles. Let's see. What is 96 about? Article 96 is about mobile phones, but it looks like our article is about recipes and soft herbs. So not a great recommendation, right? And as I think David was saying, it latched on to write words that were in the training data that was shared between this article and the training data. So your recommendation engine, your model won't break if the articles aren't actually similar. But, and here's the but, it might be useful from a user experience point of view to establish some kind of thresholds where you say, okay, at this point, the articles don't really seem that similar to the query document. I probably shouldn't provide them on the website, which is okay. But that's a threshold that you could establish by testing with users. So one of the reasons I like to talk about recommendation engines in natural language processing is because a lot of this stuff is semantic, stuff that you don't really have a good answer to, like a classification model. And you have to evaluate how your users are understanding the information. So I think you talked about A/B testing earlier in the program, but a really common way to evaluate differences in search engines or trying to pick where this threshold is, you might design an experiment and run an A/B test to figure out, hey, which of these K nearest neighbors models works better for our recommendation system? Or, hey, what's this probability threshold or distance metric threshold that we should set so that users actually click on the articles? All right. So in your assignment today, you will apply these kind of search techniques to retrieve documents related to a query. So be doing the same kind of stuff in your project this afternoon. Do you guys have any questions on the K nearest neighbors, querying documents by similarity?
Do you feel like the model failed if the distances were not that different? Meanwhile, we got food and tech.
I don't think a model can ever really fail. I think it's how good it is relative. I would say if we look up at some of these other distances, let me see, the threshold is probably really, really fine. So I'd say like the best articles we got fit were still under 1.28 for the stuff that we visualized before. So that threshold is probably somewhere in that range. But we're also only looking at 400 observations too. So the vocabulary isn't massive.
So you're referring to each article as a document, and then is each word a term, or does that depend on our unit of analysis? Or, I mean, were you referring to the unit of analysis as like a term or a token?
So our unit of analysis here is at the document level, because we're comparing and searching for different documents. But the features that we've extracted to analyze those documents are tokens. And in particular, those tokens are technically n-grams because we've extracted anywhere between a unigram up to a trigram. So basically multi-term phrases.
And for this last model, we happen to use unigrams and bigrams only.
Yes, exactly.
Okay. Thank you.
No problem. All right. Let's keep going. So let's talk about how to apply a new type of word embeddings to this problem, or a new type of vector representation. So what we've learned about so far are the kind of classic methods, count vectorizer and TF-IDF vectorizer. But those things disregard context entirely. Just out the window. So what we want to do is maybe it's actually useful to preserve some of that context, but it's harder to do. I need some more sophisticated modeling techniques to do that. Enter word embeddings. Word embeddings are typically trained using a deep neural network. And what they do is they create a dense vector representation of a document that preserves the contextual information. So you know, like our vectors from a document, they're based on the terms. So we learn a vocabulary and we count the occurrences of those words against that vocabulary on each document. What these deep neural networks that are word embedding models are designed to do is predict a context vector. So you're going to get real valued vector of so many elements. It might be 128 elements or 300 elements, whatever the model is designed to do. And the models have much more context information, but we lose interpretability of an individual feature. However, these word embedding models work really, really well on a lot of different tasks. Everything from document classification to machine translation, all kinds of fun stuff. So word embedding models are probably what you want to try if you're dealing with lots and lots and lots and lots of documents. There's a but here though. To do word embeddings and train word embeddings, you have to know about neural networks and that process, which we're going to talk about next week and the week after next. So we're going to use this thing called transfer learning. We're going to take someone else's pre-trained neural network and use that to predict a word embedding vector. Now, we don't have to do anything fancy to do that. We can use Spacey, right? I mentioned that Spacey yesterday, we were downloading a pre-trained neural network. Now, that neural network is capable of multiple tasks, one of which is predicting a context vector or an embedding. I'm actually going to switch up this section just a little bit here. And what I want to do is I want to skip down to how we do this in Spacey, and then I'm going to come back to this intro material. So Taylor asks a really adept question. So what are the different levels of analysis? Tokens the smallest, n-gram is made up of multiple tokens. A document is made up of n-grams and tokens. A corpus is made up of documents. Where does a vector fit in? A vector is some way of counting the occurrences of tokens, n-grams, or words within a document. So it would be between n-gram and documents. Or a vector could equal the documents. Basically, a vector represents a document, so they could be equal to one another. All right, let's scroll down. Again, I'm going to come back to some of this material. We won't go through all of it, but I just want to skip to show you guys how to do this in Spacey. And yes, you've already seen this. I'm so glad Jonathan brought this up. If you remember you used Basilica before in your last part of Unit 3, you just passed in tweets and got back the list of numbers. Spacey we're going to do the same thing in Spacey. We're going to pass in a document and get back a list of numbers. We'll talk today a little bit more about what those numbers represent, but you won't really understand what the numbers represent until we get into neural networks. So add a little bit more over the next 2 weeks. So again, we're going to load our model, our Spacey model. I have a sample sentence here, 2 bananas and pajamas. If I want to get the vector for this document, right, the beautiful thing about Spacey is all I have to do is run NLP on that document and then type doc.vector, and it's going to print out the vector. Amazing. This vector is 300 elements long. So just one tiny thing in Spacey. You have to use the medium or large Spacey model in order for these vectors to be the product of a neural network. Some of the stuff in the small API doesn't play nicely. So I recommend using a medium or large. Then with this vector, we can do things like similarity. Spacey allows you to just do similarity by calling on doc1.similarity of doc2. Cool. But if I really want to show you the power of word embeddings, right, the whole idea of word embeddings is they preserve context. They preserve context. So I've written some code here. You don't have to worry so much about the PCA. But I have a list of words: car, truck, SUV, race, elves, dragon, sword, king, queen, whole bunch of fun stuff. We're going to run these through our Spacey model and get vectors for them. And then for all the vectors we extract for each of those words, I'm going to run PCA to visualize these words in 2 dimensions. Okay. And let's plot how similar these words are. So now what you can see is that king, prince, and queen, all very similar, right? We predicted a context vector, we reduced the dimensionality of that context vector, and now we're seeing the similarity between words in 2 dimensions. King, prince, queen, all very similar. Truck, car, and SUV, very similar. Race, very similar to those words, as well as horse. Our big cats are all close together. Dragon, sword, and elves, also pretty close together. Potato, I don't know, it's just hanging out over here. I don't really have a good explanation for potato. This is powerful. When you start to scale this up to documents instead of individual words, now you have the context of an entire document. That's why it works so well when you use Basilica in Unit 3. These word embedding models work well. Yeah, and our model was already trained. Yeah, to Jonathan's question, the Spacey model was already trained on thousands of documents. Yep, so we're using a pre-trained model. Crystal asks, how is the context calculated? Is it proximity to similar words? The context is, it's a prediction. Oof, let me try to think of a good way to phrase this, Crystal. Bear with me just a second. The context is estimated in such a way as to minimize error. So it's not, context isn't calculated directly because we have no way of knowing that function. Instead, what we're trying to do is estimate it in such a way that we get the best results possible. And we estimate it by just assigning some random numbers to a vector, comparing that vector to what actually occurred in the raw text, and measuring the error between our prediction and what actually occurred. So it's standard machine learning practice. We're using some kind of machine learning algorithm to estimate that context vector. But the architecture, the model of how to do that, that's all neural network. And I think to answer Crystal's question in a little bit more detail, let's take a look at one of the models. There are several word embedding models. We'll look at the very first one called Word2Vec. So Word2Vec tries to predict the context of an individual word. Most of the word embedding models today predict a context vector on an entire document. But let's take a look at the training data for Word2Vec. So consider a sentence. The speedy Porsche drove past the elegant Rolls Royce. This is our sample sentence. And with a window size of 2, what we're going to do is we're going to extract some training data. And we're going to scan the sentence left to right and say to the left and right of the center word, we'll extract words that are related. So the speedy, the Porsche, right? And then we'll scan to the next word and say speedy the, speedy Porsche, speedy drove. So we see the words that co-occur together. Okay. So we're going to extract, all of these are going to be training examples. We call this type of model a skipgram. And that our model is going to try and predict the target or center word. So we're going to pass it a word, to our model, and our model is going to try and predict the window of context around that center word. Also a slightly different way of doing it. It's called the continuous bag of words, where we look at the neighboring words and then try and predict the center word. But basically the same thing. Does that help, Crystal? We'll come back to this embedding projector thing. It's cool. The model is predicting collocations. The model is trying to predict the context. Okay. So there are quite a few, I was making reference to, there are quite a few different word embedding models. So if you guys want to write this down in your notes later on, Spacey uses a model called GloveV, G-L-O-V-E, Glove, for its word embeddings. There are several other major models that are out there that are really, really good. One of them is called BERT, another is Elmo. Yes, they are Sesame Street themed. There's also now GTP2, which you could extract and use. There are some other ones out there. Those are the really famous ones at the moment. Now, I do want to talk a little bit about when you would use these versus count vectorizer and TF-IDF vectorizer. So you're probably thinking, it's like, okay, JC, these look great. This word embedding thing looks awesome. I can predict a great context vector. I can do some really good text mining with this. But here's the complication. Word embedding models have to be trained on a lot of data. And by a lot, I mean the internet. They're quite literally trained on typically something called Common Crawl, which is representative of major news sources, Reddit, and other just like massive open online data sets. So they work well in things like online reviews, Twitter, other kind of like common internet text data sources. But word embeddings don't work well in highly specialized fields, at least the pre-trained versions. So if I was using Spacey and I was working on something like medical journals, and I was trying to do some kind of document classification or recommendation engine of medical journals, using these word embeddings that were pre-trained from another data set probably won't pick up well and work on that particular use case. And so it might be better for highly specialized use cases to use TF-IDF or count vectorizer. So when you guys are working on a text classification problem or any kind of text problem where you need a word embedding or vector representation, you should try several different representations. We're going to try this tomorrow when we move on to document classification. We'll try count vectorizer, TF-IDF vectorizer, and Spacy's embedding model on our problem to see what the results are. It's all about experimentation. Okay. Are there any questions so far on word embeddings?
I just have a question real quick. I keep hearing the word mining, and I know about web scraping and stuff, but what is mining exactly? Is that the same thing?
Yeah, so text mining, I guess it's kind of an old school term maybe, but that refers to you're trying to find some kind of insights. It's just an analogy quite literally of a mine, that like some kind of insight is a gem. I think maybe a more accurate term is text analysis. You're just analyzing text.
When people say data mining, they also mean just trying to get valuable information from it, perhaps?
Yes, exactly. That's a very good.
Okay. It might be old school. That's why we don't talk about it much in Lambda.
Right, exactly. It's just the same idea as data analysis, just a really horrible metaphor for it.
Thank you.
Yeah. Right. So we'll do a quick review of today. We blew through today's content, y'all. So today in your project, you're going to create vector representations of some Indeed data science job listings. You're going to estimate a similarity model to perform searches of job descriptions. If you haven't already, you can play with the Spacy course. I highly recommend it. I also have a book on information retrieval linked at the bottom. The book's kind of dated, but some of the information is still good. So the flow of this assignment, by the way, most of these tasks are discrete. So you do task one. Task one doesn't necessarily feed into task two until you get to the very end. These two are related. The data is in a CSV file in the directory at the very bottom. So kind of the whole idea too is I want you to clean up the data, analyze the job listings for data scientists. They're maybe about 1.5 years old or so. And visualize some of the common terms. There is kind of one thing that's hard about the assignment. I want you to use a new package called Beautiful Soup. Why? Because the data is in kind of a messy format, and Beautiful Soup will help you clean up some of the HTML. All right, and just to get you started, because we actually do have quite a bit of time today, so we'll read in the CSV file. Yep. The Beautiful Soup is used for parsing HTML or XML. So the reason that we want to use it today is because we look at this data frame and see there are all these HTML tags in our description that we want to get rid of. So the best way for you to do this is to write a function. We'll call it clean description. Okay. So in order for you to parse HTML, you have to create what's called soup from Beautiful Soup. You can specify a parser. The XML parser actually typically works better than the HTML parser. Still works on HTML. Then once you instantiate the soup, then you can access things in HTML classes. So we're not going to dive too much into HTML. Don't need too much of a refresher from Unit 3. Mostly what you want is soup.text, and get text, and it'll return all the text from the job listing. Now we'll create a new column called clean description. It'll be df description dot apply clean description. Now let's take a look at our data frame. Now you can see that our clean description is free of all these messy HTML tags. But you'll also notice there are some fun encoding errors. So if you wanted to clean up the encoding errors, you'll have to do some research there as well. I won't give you, I'll let you figure that one out if you want to. But by the way, sometimes in text data, you can use your tokenizer hint to clean stuff that doesn't make sense directly, like encoding errors. Okay. I'm going to copy and paste this function to help you guys get started on the assignment today. All right. Any other questions on today's content, on today's assignment? All right. One last thing, I will be doing office hours today. Let me pull up my calendar real quick to tell you guys the exact time. Office hours today will be at 1 p.m. Pacific time. We'll do office hours for about an hour. You can come and go as you please, totally optional. If you guys don't have a lot of questions during office hours, I'll go over yesterday's assignments and we'll kind of talk through my approach to that assignment. All right. Cool. Well, thanks everyone for joining. I'll let you go a few minutes early. Kick back, enjoy lunch. We come back tomorrow, just a heads up. Tomorrow is a little bit more intense because you're going to be doing an in-class Kaggle competition. And so you'll be working. I'll lecture for a few minutes, then you'll do work for a few minutes, and then I'll lecture and then work. So tomorrow's class format's a little bit different, so just be prepared for that. Make sure that you are able to follow along in the lecture tomorrow. Should be a good time. Cool. Thanks everyone for joining, and I'll see you either in office hours or tomorrow morning.